Good morning, y'all. I have an interesting problem for you that uses a slightly different technique. And we're dealing with positive or non-negative integers, shall we call them. A, B, and C are integers greater than or equal to 0. 0 is okay, but we're not working with any negative integers here. Now we're actually trying to maximize this expression right here, subject to a constraint. So we want to know how big this AB plus BC can get if we're fixed in on this constraint, which says the sum of the three numbers A plus B plus C is equal to 56. All right. Now it turns out a very useful technique right here is to actually redefine A, B, and C in terms of X, Y, and Z. And so we actually let A equal to X plus 1. And this is not something I would have ever discovered on my own. We let B is equal to Y plus 1 and C is equal to Z plus 1. All right. Now, it follows pretty quickly that X plus Y plus Z gets knocked down to 53, right? In other words, we have A plus B plus C is equal to 56, and then X plus Y plus Z is equal to 53. That turns out to be pretty useful, and you'll see that in just a moment here. Now, so we rewrite everything right here. AB plus BC, we just express it in terms of what it's all equal to based on these substitutions here. All right. And so when you expand all this out, now I left out a ton of work here, but when you expand all this out and collect like terms, you end up with this piece right here. All right. You end up with that piece right there. And you can verify that, but I did double and triple check it. All right. Now, the only peculiarity here is that you have this 2y, right? We already know that X plus Y plus Z is 53, right? X plus Y plus Z is equal to 53. And so that means that the 53 gets written there. That you can literally think that that's X plus Y plus Z. All right. And then you have to leave this Y here because you have to take care of it, right? There's a 2Y right there, right? Okay. Now this becomes a product very quickly. You know, when you don't know what else to do, you factor, don't you? So these three terms here, here, and here contain a y, so you can factor that out and you get this expression. And here's where I got stuck until I found out about Mr. Michael Rozenberg's technique here. Now, so the idea is to relate this product to a sum, and you'll see why that's important. And that's done by something called the AM-PM. Let me write that down. We're going to use the AM. That stands for arithmetic mean. Okay, we're going to use the relationship between the arithmetic mean, what we call the geometric mean. Now, the geometric mean deals with multiplication. The arithmetic mean deals with addition. And so what we're going to do right here is show you why all of this is actually works out this way. You can write down y plus the quantity x plus z plus 1, right? All over 2. Now you guys, maybe you're used to seeing a plus b over 2 is greater than or equal to the square root of the product a plus b, a times b. Well, we're using that here, except we got a different b going on. So in other words, we can write this as greater than or equal to the square root. Remember, this is what we mean by the AMGM, all right? So this is the square root of the quantity y times, see how the addition is getting converted to multiplication here? It's kind of cool. And that's supposed to be a z, folks, despite my best attempts. Okay, so x plus z plus 1 right there, right? Again, we've seen this. It doesn't really get taught that much in a lot of schools, I don't think, you know, really. But so anyway, this relates a sum, here's a sum plus to a product, right? And it's known to be greater than or equal to. It's equal, by the way, which will come in handy exactly when y is equal to x plus z plus 1. That's when the equality actually holds right here. But you can see that if you square both sides of this, all right, you get exactly this statement right here in reverse, right? Okay, see, it's just, you can see the inequalities are kind of flipped around. This would be on the other side, right? But when you square this object, you get exactly this object right here, right? And so that's why we could start turning the equalities, all of these equalities now becomes this inequality right here. You see? It's just this guy right here in reverse, right? Okay, now, so all's well. And so what we do right here is we already know that x plus y plus z is equal to 53, but this says x plus y plus z plus 1, right? So that's where this 54 comes from. That's where the 54 comes from. And so when you do the arithmetic on this, you actually get 784. But that would be the maximum if these were real valued, but we're dealing with integers. Now, what you can do is, like I said earlier, you would set, let me see, do I have room right here? Set y equal to x plus z plus 1. Okay. Now you'll use that in conjunction with the fact that x plus y plus z is equal to 53, right? And I'm not going to show you the arithmetic here, but x plus y plus z is equal to 53. And so you can work that in here, using substitutions. And what you'll end up getting is that this implies that b has to equal to 26. And again, it's not too hard to show that. I'm just trying to avoid the clutter here. Okay, that implies that b has to equal to 26. And so the solution here, and I'm going to wave my hands a little bit more, there's the 26 you see, right? And again, you guys can verify this on your own if you want to, in conjunction with this piece right up here. All right. But notice that this is a standard result. You maximize something when it's a square, right? Or notice that 15 times 15 is bigger than, say, 16 times 14 or 17 times 13. It's just a square versus a rectangle sort of thing, And so you know that these two have to be 15, all right? Now, again, if it were real valued, you would, the answer would be 784, but these were the largest integers that would meet the criterion. If you bump these integers up any higher, you would exceed this value 784, right? Okay, and again, I'm leaving out some of the arithmetic, folks, but this is the solution. And notice that these add up to 53, right? 56, my bad. 26 plus 15 plus 15 equals to the 56 that you see right there, right? Again, the sum of these is equal to 56, which is part of the constraint. And you can see why we can't go any higher. That definitely is going to push it above 784, right? So anyway, folks, this the answer to the question is this, all right? That part right there, and then I hope you like that. I mean, I thought that was super cool, just that substitution, then using kind of this unsuspected usage of the arithmetic mean, geometric mean inequality. Let me know if you have any questions.